Hi, in this video I want to have a look at the link between differentiation and integration. So if I have a function of x and I differentiate or find the derivative, I end up with a derivative function. If I have a derivative function and I integrate it, I get back to my original function. So that's the link between differentiation and integration, and we're going to have a look at this with just a simple scenario of a car accelerating from a station. So the scenario we have is a car accelerating at a constant rate from a stationary position until it reaches a speed of 28 meters per second. Okay? And 28 meters per second is approximately equal to 100 kilometers per hour. After that, it travels at a constant speed of that 28 meters per second. It takes 4 seconds to do this. So you can see that my change of velocity according to my time is a constant steady rate, and so the rate of change of that's going to be my acceleration. Now I can write a rule for this. If I have a look, that my velocity according to time is 7 times the time, because for each second that it's travelled, my velocity has increased by 7 meters per second. That's for the first 4 seconds, and then after that, my velocity is at a constant rate of 28 meters per second. Now, if we're looking at what this would be like as a derivative function, or as a time function, initially, as my car is travelling at a slower speed, the rate of change of distance is going to be fairly slow, and then as the car picks up speed, it's going to change distance or increase its rate of distance at a faster and faster rate. This slide is showing me the same travelling of the car, but now I'm looking at the distance according to the time. So remember we said that initially as the velocity was slow, the distance travelled was at a slower rate, and then it steadily increased until at 4 seconds it then kept on at a linear rate because its speed was travelling at a constant rate of 28 meters per second. So the graph I have here, the distance according to time, and I don't know why I've got an X there, we'll change that to a T, is 3.5 times the time squared. So we can see that we've got like a quadratic curve happening here for the first 4 seconds, and then after that it's increasing at a steady rate of 28 meters for each second travelled. So how does this link in? Now we know that before that if I had a distance time graph and I found the derivative of that, that gave me a velocity time graph. So we're going to explore that a little bit further. The next thing we're going to look at is another aspect of finding the integral or integration. So if I look at this, here's the first part of this graph. Now this time I've found a shaded area between my function and my x-axis, and it's a triangle. It's not always going to be a triangle, but here it's a triangle. So how could we find the area between our function and our x-axis? Well, area is a triangle, so it's base times perpendicular height divided by 2. So our base is the time taken, okay? And so from 0 to 4. And our perpendicular height is 7 times the time, because that's the function that's represented by the y-axis, the velocity. We said that that was 7 times the time. So this seems fairly straightforward. If I wrote it as a rule, that my area is going to be the time times 7 times the time, so that's my base, and that's my perpendicular height, divided by 2, which gives us 3.5 times time squared. So if we plugged in our values, our time is going to be 4 seconds, and 7 times the time is 28. Divide that by 2, and that's going to give us our answer of 56 units. So the area between our function and our x-axis from 0 to 4 seconds is 56. I'm going to go back to have a look at our distance time graph. Can you see that at 4 seconds, the distance travelled was 56 meters. And if we also have a look back, we said that the function for the area between the function and the x-axis is 3.5 times the time squared. And we have a look at our distance function, it's 3.5 times the time squared. So integration not only will give us the function for our distance time on our velocity time function, but also gives us the area between the curve. So as a recap, if I've got a function, so my distance time function, and I find the derivative of that, I get the derivative function, which, if it's a distance time one, it's a function of the rate of change. It gives me a velocity time function. And if I use the velocity time function and I go back the other way and I find the integrate, so find the integral of that, I'm going to get my distance time function. The other thing that the integral also gives us is the area between the function and the x-axis. And we're going to explore that a little bit further. There's some other conditions, but this is just a simple example to show how the two are linked together.